All right, what if I told you there's one single, powerful idea, a kind of master key, that can solve a whole bunch of really tough coding interview problems? I'm talking everything from finding a value in an array to, optimizing a shipping schedule. Today, we're not just talking about the binary search you learned in school. No, we are unlocking the secret to a huge class of problems. So yeah, let's get right into it.
So, you know the basics, right? Find a number in a sorted list. Easy. But what about finding the first bad software version out of a million deployments? See, your standard textbook binary search, it kind of falls apart there. The target isn't some number you're looking for, it's a concept. It's that first moment something went wrong. And this, right here, is where most people get stuck. But it's also where binary search gets really interesting and powerful.
And that's exactly what we're going to do today. We're going to pull back the curtain and reveal that one core secret, the thing that transforms binary search from just a simple lookup trick into a full-blown problem-solving framework.
Okay, so here it is, the big secret. The most crucial thing you need to understand is this. Binary search isn't really about arrays. I know, that's where we always see it, but that's just its most common use case. At its very heart, binary search is about one thing and one thing only: finding a boundary.
Yeah, this is the definition you want to burn into your brain. A monotone domain sounds super technical, but it's not. It's just any space where a condition, once it flips to true, it stays true forever. The domino analogy is perfect here. You've got a line of them. Once one falls, all the rest are going down too. Our job is just to find that very first domino that tipped over. Think about it like this. Picture a giant, long row of light switchers. Way off to the left, they're all off. They're all false. But then you hit a certain point and bam, one switch is on. And every single switch after that is also on. All true. That point where it flips from off to on, that's our boundary. And binary search, it's just the absolute fastest way to find that very first on switch.
And the beautiful thing is the algorithm is always the same. It doesn't matter what the problem is. It's always 3 steps. 1, you pick a midpoint in your search space. 2, you check your condition. You ask the question, is the switch on or off here? And 3, you just throw away the entire half where you know the answer can't be. You just keep doing that, chopping your problem in half again and again until you're left with just one single point. It's simple, it's elegant, and it is blazing fast.
All right, so let's start with what we all know, right? The classic sorted array. We can think of this as our first toolkit, the precision toolkit. And it's all about one thing: pinpointing a specific spot with, well, incredible precision.
So you've got your basic exact match. Super straightforward, find the number. But it gets way more useful when you have duplicates. Lower bound helps you find the very first time a number shows up, which is crucial if you need to find, say, the start of a specific data range. Then you have upper bound, which finds the last one, maybe to find the end of that same range. And insert position is an absolute must-have for anything that needs to keep a list sorted on the fly. These are really your foundational, high-precision tools.
Okay, now for the fun part. Let's build on that foundation, because this is where binary search goes from being just a helpful little tool to an absolute superpower. We're about to make a huge leap. We're going to stop searching for an index in an array and start searching for the answer itself. This is our abstract toolkit, and it's all about discovering some unknown optimal value.
The pattern is famously called binary search on the answer. And the key shift is that your search space isn't indices anymore, from 0 to n-1. Nope, it's a range of possible values. So imagine you're looking for the best shipping capacity for a truck. The answer could be anything from 1 pound to like a billion pounds. We are going to binary search that entire massive range of possible answers to find the one perfect solution.
This quote just nails the idea perfectly. I want you to visualize a ruler. And this ruler represents every possible answer stretched out from a really small guess on one end to a huge guess on the other. What do? You check the value right in the middle of the ruler, and you ask a simple question. Is this answer feasible? Does it work? If the answer is yes, awesome. But maybe we can do even better, right? So we throw away the top half of the ruler and search the bottom half. If the answer is no, well, we know we need a bigger value. So we throw away the bottom half and search the top. You just keep cutting that ruler in half, over and over again.
All right, let's make this real with a classic problem you might see in an interview: Coco eating bananas. The setup is simple. Coco the monkey has to eat a bunch of bananas within a certain time. Our job is to find the absolute slowest speed she can eat at and still finish on time. So all the possible speeds she could eat at, that's our new search space.
Okay, so we pick a random speed from our range, let's say 30 bananas per hour. Now we ask our question. At this speed, can Coco finish all the bananas on time? We do the math and yes, she can. Awesome. But remember, we're looking for the minimum speed. Since 30 works, any speed faster than 30 is totally irrelevant, right? We already know they work. So we can just throw away that entire upper half of our ruler of speeds and search for an even slower, more optimal answer in the lower half.
So we just keep narrowing it down, always checking the midpoint of what's left. Let's fast forward a bit. Say we've narrowed it down and our next guess is a speed of 4. Is that feasible? We check. Yep, it works. So we know the answer is either 4 or something even smaller. So we try the lower half again. How about a speed of 3? We check again, and nope. At a speed of 3, she runs out of time. And there it is. That's the aha moment. We found the boundary. The condition, is this speed fast enough, just flipped from true at 4 to false at 3.
And that's our answer. It's 4. That is the smallest possible value. It's that first domino to fall, where our condition, is this speed feasible, is true. And think about what we just did. We weren't searching through an array. We were searching through the abstract idea of speed to find that single optimal boundary.
Okay, great. But what happens when the data isn't in a nice, simple, sorted list? Well, guess what? Binary search is still your best friend. You just have to be a little clever and adapt the logic. Let's take a rotated sorted array. At first glance, it just looks like a jumbled mess. But there's a hidden trick. No matter where you pick your midpoint, one of the two halves has to be perfectly sorted. It just has to be. So your first job is to figure out which half is the normal one. Once you know that, you just ask a simple question. Could my target number possibly be in this nice sorted half? If yes, great, you search there. If no, well then you know it must be in the other, messy half. But either way, you're right back to doing what binary search does best, eliminating half the problem in a single step.
Or how about finding the peak in a mountain array? You know, one that goes up and then comes back down. This one's actually even more intuitive. All you do is look at your midpoint, and then you just peek at the element right next to it, mid plus 1. So are you on an upward slope? If you're going up, that means the peak has to be somewhere to your right. If you're on a downward slope, the peak has to be to your left. It's like you're hill climbing, but you're doing it with the crazy speed and efficiency of a binary search. All right, let's talk about the part that can literally make or break your technical interview. Because knowing these patterns is one thing, but writing clean, bug-free code when you're under pressure, that's a whole different ballgame. This is a pretty famous quote from Joshua Block, an absolute legend at Google, and you should really take it as a warning. He pointed out that for years, even the official binary search code in Java's standard library had a subtle bug, a bug that almost nobody noticed. It just goes to show you, the little details here matter a lot. And this is that exact bug. The classic way to find the middle, low plus high divided by 2, looks fine. But if your low and high pointers are really, really big numbers, like way up in the billions, adding them together can actually exceed the maximum value an integer can hold. This is called integer overflow, and it can cause your program to crash or just act super weird. The fix, on the right, is mathematically the exact same, but it avoids that huge addition, which makes it totally safe. Just always use this version, no exceptions.
So before you write a single line of code in an interview, run through this mental checklist. First, state your loop invariant out loud. What's the one thing that's always true about your low and high pointers? For example, the answer is always between low and high. Saying this keeps your logic straight and helps you avoid those nasty off by 1 errors. Second, pick the right termination condition. Low less than or equal to high is your go-to for finding an exact match, but low less than high is often safer and easier to reason about when you're looking for a boundary. And finally, and this is huge, always think about edge cases. What happens with an empty array? What about an array with just one element? What if it's all duplicates? Nail these and you'll look like a pro.
So, let's zoom out. What's the big takeaway here? If you walk away with just one thing from all of this, I want it to be this fundamental shift in how you think.
Binary search isn't just some algorithm you memorize. It's a mental model. It's a way of thinking, a way to zero in on any answer by repeatedly asking a simple yes or no question and then throwing away half of the entire universe of possibilities. We've seen how this applies to simple arrays, to complex optimization problems, even to weird data structures. The real question, the one I want to leave you with, is what other problems can you now see as a search for that single critical boundary?